All right, good morning. Hello, everyone. Welcome to the first High Energy Density Science Seminar of 2026. I'm Federica Copari, the chair of the HED Science Seminar Series, and I'm pleased to introduce today's speaker, Dr. Veronika Kruse from Lawrence Livermore National Laboratory. Veronika received a PhD in theoretical nuclear physics from the University of Arizona in 2012. Soon afterwards, they moved to Livermore and joined the Nuclear Theory and Data Group as a postdoc, where they performed nuclear structure calculations of light ions to test quantum chromodynamics-based nuclear potentials. In 2015, Veronika was converted to a staff member in the plasma modeling and theory group, where they worked extensively with Carlos Iglesias on questions related to the iron opacity experiments. Veronika has also worked in the ICF program, supporting the work done by the Cognitive Simulation Group, as well as being a technical fellow of the lab's Center for Global Security Research. In the last 2 years, Veronika has been an APS Center Mentoring Fellow, and as of this year, a member of the Executive Committee of the APS Far West section. Today, Veronika's talk is titled, "Can we resolve the discrepancy in solar modeling with updated opacity models?" Before we start, I want to remind everyone that this talk is being recorded, and if you're not comfortable with that, feel free to log off or leave the room. Also, this is an unclassified hybrid meeting open to external participants, so please be aware of export control issues. In-person participants, please wait until after the talk before asking questions so that I can pass the microphone to you. And online participants, feel free to type your questions in the chat and I will read them for you. With that, I hope you enjoy today's talk. Veronika, please take it away.
Yeah, thank you very much, Federica. It's so lovely to see that the first seminar of the year has filled up a large part of a room with people still coming in. If you happen to be dialed in at the lab, there is some form of coffee from what I've been told, but there are very tasty cookies. So Federica and I are essentially office neighbors, and sometime last year in September, she came to me and said, "You are going to give a talk in the HD seminar series." And eventually she twisted my arm, and today I am here to talk a bit about something that I've worked on for quite a number of years, as the introduction said, with Carlos Iglesias. So it's actually an honor to finally be able to present some of his work, as well as talk about some of the work that the opacity group at the lab here does in general, as well as our collaborators in the National Opacity Program at Los Alamos and Sandia National Lab. When I first came up with this title, I had these grand ambitions to talk about why opacity is important at the lab, why it is also important in astrophysics. Upon reflection, I may have bitten off more than I initially assumed I could tackle in a 1-hour talk. So what you will hear is really an interesting set of experiments that were done over the last 10 to 15 years, how we've tried to understand these experiments, what some of the theoretical challenges have been in trying to explain these results, and why some of that is interesting to the astrophysics community. So as Federica said, there's a lot of material, so please ask questions at the end. Hopefully we get through much of the presentation. So to begin with, here is a picture of the sun. The sun, in some sense, is a fantastic laboratory for high energy density physics, as well as plasma physics, everything we typically see at the DPP conference in October and November. It's probably not super clear here, but if I can get this cursor to work, you can see there are these bright spots in the sun, there are these darker spots. There are actually no sunspots present in this plot. There's some flares over here. There's a lot of interesting physics going on. I'm just going to change my cursor to a laser pointer. Now we can do a bit better than this. We can actually look at this emission spectrum and break it up into the frequency components of the sun. So what someone has done here is actually looked at the visible part of the spectrum of the sun and broken it up into all the different colors we see. Each strip covers 60 angstroms, and there are 50 of these strips, and this is most of the visible spectrum of the sun. If you look very carefully, you'll see there are always black vertical lines. These black vertical lines correspond to absorption lines in the solar spectrum. And those absorption lines indirectly tell you which elements are present in the sun. Now, this was probably pretty common knowledge to most of us that have taken PhD level physics classes, but this, for example, is how we discovered helium. Now, bonus points if someone can point out where the helium lines are. I didn't actually know this. They're probably around here in the yellow. Helium was discovered in 1868 through a solar eclipse by doing a technique like this, but it took another 30 years before it was discovered on Earth. Okay? So even spectra like these, which we would say is ancient physics these days, tell us a lot about the sun and is actually very valuable information. We will get back to this plot closer to the end of the talk. But we can go even further about understanding the sun. So helioseismology is what helioseismology measurements tell us the location of an interesting part of the solar structure, namely in the interior of the core. It is radiation dominated. The energy is transported by radiation. As you move closer towards the outer parts of the sun, it cools, the densities get a bit lower, and eventually convective mechanisms take over to transport the energy out of the sun. Now, the location of this boundary, known as the radiation-convection boundary, is determined through something called helioseismology, just a bit of a fancy word. Helioseismology is looking at the acoustic vibrations of the sun. These vibrations are in the microhertz range, and there are many hundreds to well over 1,000 modes that have been observed. That information is inverted to give you a sound speed profile. And if you look at that sound speed profile carefully, you can reveal where this radiation convection boundary is. I don't have any good pictures on how this is exactly done, and I must admit only in the last few days have I read up more about this. I'll give you a reference at the end where you can look up about that. But through doing things like this, we learn about the structure of the sun. So for example, we know deep in the inner core, the center of the sun, the temperatures are about 1.3 keV. If you're unfamiliar with electron volts as a temperature, the conversion is 1 electron volt is about 11,000 Kelvin. We know the electron densities are about 6 times 10 to the 25 electrons per cubic centimeter. If you're a student watching online, these are approaching ICF-like conditions that we see on NIF. Further out where the radiation convection boundary is, the temperatures are about 200 eV, densities of about 10 to the 23 electron per cubic centimeter. And these two set of numbers are what you need to keep in mind the rest of the talk. Now, as I said, we can measure the location of this boundary quite precisely. We know it's about 0.713 of the total radius of the sun. As you can see, the uncertainty behind that is tiny. However, we can run something called a standard solar model, where we basically start the sun off 4.5 billion years ago. We evolve this model, and then we ask the question, do these solar models actually reproduce where this boundary is? And the answer is, depends. Currently, we predict this boundary to be at 0.72 versus 0.71 total radius of the sun. And that's about a 13 to 15 sigma deviation, which is large. In the 90s, we could do this way, way better. Now, what changed between the 90s and now? Well, a whole bunch of things, but one of the biggest changes is that the solar abundances had been revised throughout the 90s and then into the early 2000s, and they keep continuing to be revised. And the most significant change is that the metal fraction in the sun was significantly lowered in the early 2000s. So one way you can fix this problem is you raise those metals back up, or point 2 here, you have to increase the opacities of the metals, things like iron, neon, and oxygen. Now, if you're confused, why is oxygen a metal? In solar structure, everything that is not hydrogen or helium is a metal. And it's often denoted by the letter Z. So moving on. Closer to home, in 2015, Sandia, through Jim Bailey, publishes what we call the iron opacity experiments around here. And this result is going to go down in history as one of the most important papers that came out in opacity research. So on the right here is essentially a screenshot of the Nature paper results, and they show 4 different conditions. The experimental data is shown in red. It's a function of wavelength, and what is plotted is the opacity. And in blue is one of the opacity models that we typically use called SCRAM, developed by Stephanie Hansen, who used to be here now at Sandia National Lab. Okay, and these panels going from bottom to top increase in temperature and increase in density. So this is, a mild 165 eV here, density of 0.7 times 10 to the 22 electrons per cubic centimeter. And at the top, you're at 195 eV and a density of 4 times 10 to the 22. As you see, as the temperature and density go up, suddenly the opacity is much larger than the models predict. Now, you might say, okay, maybe Scram is incorrect, but all models have this problem. All theoretical models tend to agree with Scram. Scram is just one of the possible models we could have run. And at the time, no models could actually explain this large discrepancy. Now, this was kind of puzzling to us because in 2007, on the same platform, there was another opacity experiment done at slightly lower temperatures, 150, 155 eV roughly, lower density. In this case, the experimental data is in red. The models are in red and the experimental data is in black. And if you look at this, wonderful agreement. This is actually fantastic agreement. So how come these conditions, all models describe pretty well, but the slightly higher density, higher temperature conditions, suddenly everything breaks down? This has been a big puzzle over the last 10 years and continues, in some sense, to be a bit of a puzzle. Now, much work has happened since 2015 to now, some of which I will touch on here. I can't possibly give a complete history of everything that's been done, but that's kind of like where things stood in 2015. Let's see if I can I really want to get a laser pointer here. I guess we'll just use the cursor. Okay, so there are actually two related opacity problems. One is for a national lab audience, which is why do all these opacity models fail to reproduce what are called the Anchor 2 iron opacity experiments? Now, I have to introduce some terminology here. Going back to that plot I showed, the lowest panel with the lowest temperature and the lowest density we refer to as Anchor 1. Those are close to the 2007 PRL paper. If we simply just increase the density slightly, we refer to that as Anchor 1 plus. Same temperature, slightly higher density. Already problems start to appear. Anchor 2 is higher temperature and higher density, close to the radiation-convection boundary conditions in the sun. Not exactly, the density is too low, but close. And then the final panel, I think I've sometimes heard it called Anchor 3, but that's not typically things we speak about. So Anchor 1 plus is higher density, and Anchor 2 is higher density, higher temperature than the 2007 papers. The other problem is the solar model is. And their questions are slightly different. Whoops. Go back a bit here. Namely, do they have the correct physics in their solar model? And that touches a whole bunch of things. Do they have the right abundances, the right opacities, equation of state, nuclear reaction rates, diffusion models, a whole bunch of things. And they've been testing all these things to check what matters and what not. But the abundances and the opacity seem to be driving this discrepancy on where the location of the radiation-convection boundary is. And on the right here, I've just shown, for example, one of the tests that are typically done. It's a plot of the relative sound speed versus a calibrated model that gives you the correct location of the radiation-convection boundary. In this case, they have assumed one set of abundances, one equation of state, and they've just varied the opacity models. In green, for example, here you see the opal tables being used, which were developed here, as well as some others like the opacity project and the Los Alamos oplib tables. And although this looks like a 1.5% discrepancy near the radiation convection boundary, maybe not that large, it is large for the solar model is. Okay, so quick outline of a presentation. There are students dialed in from our UC campuses. I want to talk a bit about atomic processes and what they have to do for opacities. Why is iron interesting to the context of solar modeling? I worked quite a lot on point 3 and 4, which are there other processes that we typically don't put in opacity tables that could explain why the opacities are too low relative to the experiment? I do hope to touch a little bit about the issues the solar modelers face. And then I'll wrap up with some final thoughts and some conclusions. So atomic processes, I assume most of us are quite familiar with this. You have a plasma, the plasma is quite hot, it's dense, Inside the plasma are a bunch of elements. Let's take iron as an example. They exist in a whole host of different charge states. Each of those charge states we need to calculate a set of cross-sections for. Assume that there is a Planckian distribution of photons coming in. Some of those photons will excite bound-bound transitions, where a photon is absorbed, say in an inner orbital, kicks up an electron to a slightly higher orbital. That's one cross-section we need to calculate. If your photon is energetic enough, it can kick the electron out of the atom or out of the ion. We call that bound-free. Free-free is basically you have an electron that's near an ion. It absorbs a photon, now has a higher kinetic energy. And then there is a small contribution from scattering, where a photon comes in, scatters off an electron, kicks the electron up in energy, but then the photon has lower energy left. All of these processes are included in opacity tables, and it's very well understood how to calculate these cross-sections. Now, what does that have to do with opacities? If you send this Planckian distribution through some sample, some part of it is absorbed as a function of frequency, and the thing that comes out at the back, the transmission spectrum, is related to the opacity through the optical depth in this exponential decay. This tau is the optical depth, which depends on the frequency that you're looking at. The optical, and I should say, this exponential decay is called the Beer-Lambert law. The optical depth is a product of the areal density, rho times the path length L that you went through, multiplied by the frequency-dependent opacity kappa. And since this needs to be dimensionless, you can infer that opacities have units of centimeters squared per gram or area per mass. I want to point out, just for the students that may be listening, this reference down here by Jim Bailey in Physics of Plasma, it's a tutorial type paper, is probably the single best reference you can read on how, what the general physics behind opacities are and how they are measured in the lab. This paper, I was very thankful to see when I joined the opacity and modeling team, because it instantly told me everything I needed to know and got me going. So if you want to read up more, read this Jim Bailey paper from 2009 in Physics of Plasmas. Talking about Jim Bailey, here is a picture of him. He gave a seminar in the series about 2 years ago. I don't have time to talk about how opacity is measured in the lab. This is up on YouTube. Remember to like and subscribe. I clicked like, so it's at least one like now. You can find this on the lab's YouTube channel, Inside Livermore Lab, or you can head to the HED Center website and poke around there, and you will find the link to the YouTube platform where many of our seminar talks are present. So why is iron interesting in the solar models? Well, let's talk a bit about what the sun is made up of. It's overwhelmingly hydrogen. So why is hydrogen not playing a role? Well, hydrogen at these conditions is essentially fully ionized, so the only process you need to consider is free scattering. Free scattering is just a smooth background as a function of energy at these conditions. And in black here is a representative frequency resolved spectrum of the opacity at the solar radiation convection boundary. So you can see that hydrogen doesn't really give you any of a structure. Well, what about oxygen? Oxygen plays quite a role. Oxygen is ionized into the K-shell, so you have bare oxygen, hydrogen, and helium-like oxygen that you need to calculate. That gives you some of the structure, which are these K-shell transitions you're seeing, as well as the bound-free, the smooth bound-free background. Okay? So you start to pick up some of these peaks here. Lastly, there is, oh, and I should point out, recently there was a PRL in November by Jim Bailey and collaborators on measuring the oxygen opacity in these kind of environments. It was featured in Physics as well as an editor's suggestion. And then moving on to iron. Iron is only ionized into the L shell, so you have typically 10 electrons still bound to the nuclear charge. Now you have a lot more structure, a lot more bound-bound transitions you have to calculate. There's bound-free that comes from various charge states up here. It's probably a small free-free contribution as well. But you can see the structure becomes much more complicated. And iron plays a big role in the opacity at the solar convection boundary. I should also say, I kind of hinted at this earlier, it's not just one charge state you calculate, you actually need to do this for a host of charge states. So if we look at the Z experiment that was performed, for example, this is the fluorine-like charge state up here. It's the most dominant one. That would be neon-like. There's oxygen-like. So each of these charge states, you need to have a model that gives you that charge state distribution, and then for each of them, calculate the corresponding opacities and weigh them by this distribution. And in case you're curious, what are these other curves? So you go deeper into the sun, you start to ionize iron more and more. So the charge state distribution moves to the right, meaning the ions are more and more ionized. Okay, so that was a quick introduction over there. Why is iron important? It contributes 20% of the opacity at the solar radiation convection boundary. In the middle plot here is a plot of the abundances on a log scale of all the elements in the solar composition, overwhelmingly hydrogen and helium. And then you see oxygen, neon, and iron, down at like the sub 1% level. However, if you ask the question, which of these elements contribute to the opacity, turns out it's actually oxygen that matters the most, at about 25%. Iron at about 20%, and neon at about 12%. And there's hydrogen, a mere 10%. Even though hydrogen is the dominant element, plays a relatively minor role relative to the metals. That's why we care about iron and oxygen. And if we could, I suppose neon. Okay, so I worked on something which is going to be a little technical, so I've tried to make this accessible for everyone, which is something called two-photon absorption. Soon after the paper was published, Carlos Iglesias pointed out, hold on, the experimental data seems to have a bit of a problem. That is, if you plot it, plot the opacity and I think in red is the experimental data, and you overlay that with some theoretical calculation, this time from the topaz model, you see this very disturbing part over here. This dashed line is what the opacity should be from a cold material, not hot, dense material. Cold material is not ionized at all. There are significantly more electrons that can contribute to the bound-free cross-section. The conclusion was that since the experimental data lies above this cold curve, you actually need more electrons in the L shell than there physically can be. Okay? And that would violate something called the oscillator sum rule, which is a thing that we hold wholly in atomic physics. Now, Dick Moore actually came up with a very interesting proposition, which is, hold on, two-photon absorption does not need to respect the oscillator sum rule. What if two-photon processes are starting to play a role at these conditions? Could this explain the discrepancy? This idea was pitched right as I converted to staff. So literally day 2, Carlos, down in the auditorium here, came to me and said, we don't think this is important, but here's a fun project for you to work on. Okay, so let me just talk about, on the left is just a plot of what opacity is. I covered this earlier. Just quickly, what is the physical idea behind two-photon absorption? Remember, you need to remove photons now to increase the opacity. You take one photon out of the backlighter, and now you need to take a second photon either from the backlighter again, just illuminating your sample, or from the sample itself. So there are two sources of photons, a backlighter or the plasma itself. Okay, so you take one photon out, and now from this intermediate level here, you can then absorb another photon and end up in some final state. And this looks like a bound-free process, which was the one that we were interested in most. Now, I should say, don't be fooled by this picture and assume that you excite to an atomic level, hang out there, wait for a photon to come around, and then excite further. This is in the language of, say, perturbation theory or quantum field theory, where this intermediate level is basically just virtually there. You need both photons simultaneously to go from some initial state to a final state. This formalism was worked out by Carlos and myself, and Dick Moore made contributions in his work, as well as Jean-Christophe Paine. The idea is essentially you want to calculate the two-photon cross-section. This term in front is a correction to stimulated emission. but you need to calculate the two-photon cross-section from the two sources, the backlighter and the plasma. This is a long, tedious expression that contains something which we've called a rate constant. It tells you how quickly you go from the initial state to the final state. Has a whole bunch of prefactors. Notice the first thing, there is a fine structure squared constant. From my nuclear background, that already tells you fine structure squared is small relative to one photon. You have to conserve energy, which is this delta function. And then this D contains a lot of V nasty angular momentum you have to do. Atomic physics tends to boil down to angular momentum components multiplied by radial wave functions. These radial wave functions we call P, and they tell you to go from the initial state to a final state is a sum or an integral over all the intermediate dipole matrix elements that you can have. So just going back one slide, all the dipole matrix elements that take you to all these different intermediate states, and then from the intermediate state to the final state. And that's weighted by some energy denominator. You have to essentially do this sum. And a physical picture of that is kind of just what I said. You excite to a whole bunch of these intermediate P states. If you're starting from, say, 2s to, you go to 2p, 3p, 4p, and all of that. And then from there, you can go to a final state, which is either an s or a d orbital. Now, in principle, you have to do that sum. But turns out, if you read rather antiquated quantum mechanics books, for example, the book by Schiff in 1968, there is mention of something called the Dalgarno-Lewis method. That's a way to treat this problem exactly, so long you use central potentials. This Dalgarno-Lewis method is actually amazing in some sense. If you can do it, you can do second-order perturbation theory exactly. You don't have to do these sums. And past summer, I had two students who were undergraduates who, unbeknownst to them, actually used this method to in a 1D problem involving the infinite square well. So if I were teaching some quantum course, that would definitely be part of it. Anyway, so the conclusion, you can do that sum exactly. There's a bit more I'm skipping over. How do you actually put all of this together? As I tell my students, math is not hieroglyphics. There's physical meaning behind what I'm pointing at here. This two-photon cross-section is an integral over some photon energies, the second photon you have to pull out of somewhere, weighted by a distribution of photons at that energy, multiplied by that rate that I just calculated. Visually, here I have fixed the energy omega at one particular value, and now I have mapped out what this rate constant k is. That's this black curve you see in the background here. And every time you see a sharp peak, that's when I hit one of these intermediate states. I need to weigh that by the photon distribution from one of the sources. In blue is the backlighter source. It's 300 eV in energy, roughly. In red is the Planckian of the plasma itself at 182 eV. If I multiply one of these colored curves against this rate constant k, that's the integrand. I integrate all of that up, and then I have a cross-section at one energy. So that just tells me the two-photon cross-section at a specific energy. I, of course, repeat this over and over to map out the cross-section over all energies I'm interested in. But that's basically what it came down to. Now, you'll notice that these peaks are pretty sharp. So we have to introduce something called a line width to make sure that these quantities over here don't go to infinity. It's going back, if you're curious, you can be exactly on resonance, and then this denominator 0, this whole expression goes to infinity. You have to circumvent that by introducing a line width. We take those line widths from what we use in our opacity codes, these Demetrius and Konchevik fits, and we assign them for the 2p, 3p, 4p. That avoids these infinities. You do this integral, you map all of this out as a function of wavelength to compare the Sandia experiment, and you get this solid curve down here, where I've plotted the cross-section in megabarns per electrons. And the top thick curve over here is the single photon cross-section at these conditions. And you'll notice, this is a logarithmic scale, there's 4 orders of magnitude difference here. Conclusion, two photons do not seem to matter here. But we realized something very quickly. If we just artificially lowered the width that we assign to each of these peaks, all these peaks you see here, by a factor 10, if we just make them narrower, those peaks shoot up and they move the cross-section up by about a factor 10. And that told us something, that the assignment of these widths is actually key to this problem. Now, making these widths 10 times smaller is a little bit ridiculous. Making them 1,000 times smaller is even more ridiculous. So in this case, there's not much of an issue here. We don't think two-photon absorption plays any role in the anchor 2 conditions. But remember this point with the widths. If you want to read up about it, there are 2 papers that Carlos and I put out, 2019 and 2021. The first paper really lays out all the theory. The second one addressed some questions that were raised through an opacity workshop series held in 2020 when COVID was raging along. Recently, we've wondered, can bound-bound scattering actually explain any of this data? Scattering is also one of the processes we typically pay less attention to because we think it's small. The formalism behind bound-bound scattering looks a lot like two-photon absorption, so it was pretty quick for us to start getting into this. Why would we be interested in this? Here is a zoom of that anchor 2 panel from the 2015 Nature paper, and these n equals 4 lines. These are n equals 2 to n equals 4 transitions in iron. You'll see that the model data is quite a bit below what the experimental data is. So we thought this would be a very quick thing to check to see if scattering is maybe playing a role for these lines here. Physical picture behind scattering: you absorb a photon, you get kicked up to one of these n equals 4 states, you emit a photon, the scattered photon, back out, and you end up either in n equals 3. That would be an inelastic process, or you come straight back down to where you started. That's the elastic process. We call the elastic Rayleigh scattering and the inelastic part Raman scattering. Raman scattering is typically quite a bit smaller. You can show that it goes as the scattered photon divided by the initial photon to the cube power. And in this particular construction, that's tiny. So Rayleigh or elastic scattering should play a role here. Off I go and I load up our favorite open source code, flexible atomic code, generate a bit of atomic data for neon-like iron in the ground state, the 2p6 configuration. I calculate all the dipole transitions I need to go from n equals 2 to 4, and all the way back down from n equals 4 down to 2, 4 to 3, 4 to 4. Piece that all together. I haven't shown you the horrible equations. Calculate the cross-section for elastic scattering in red and inelastic scattering in blue, and then overlay the single photon calculation on top. Okay, and you can see that scattering doesn't really seem to play a role relative to single photon absorption. It's about a factor 50 here at the peak. Once again, depends what width I assign to these lines. We extended this calculation to look at the full spectrum, kind of like I did for two photons. And then we realized for n equals 3, with 2 to 3 transitions, suddenly this elastic scattering peak started to become comparable to the single photon peak, exactly at line center. And now our assignment of those line widths starts to become an issue. What model we use and how large those line widths impact the size of the scattering peak here. So right now, Carlos and I are looking at this much more carefully to make sure that we assign the right line widths in these scattering calculations. But if these results hold, even if this is a factor 10 smaller, it could start to indicate that scattering might play a role in some parts of the spectrum. And I'm going to pitch this to our colleagues down in Sandia, or maybe here at NIF. We can measure these n equals 3 transitions, which are not present in the 2015 plot I showed. That might be interesting for us to look at. It's of course experimentally quite difficult to do. All right, so it looks like we have a bit of time to talk about things I only half know something about, so I'm going to flap my arms like a penguin on the Antarctic ice shelf, pretend I know what I'm talking about. So I really wanted to touch parts of my solar models. What are the questions that the solar modeling community face? I listed many in the beginning, but I want to focus on 2. The story behind the abundances, and what that has to do with the opacities. Because if you ask people at the national labs, they're going to say like, well, you know, these abundances get revised all the time. One day they will come back up, problem solved. If you ask the astrophysics community, they're going to say, well, Sandia experiments seem to indicate that the opacities are off by about, 20 to 50%. That solves our problem. Who's to blame here? Turns out all of these things are interconnected. So if you want to find out more about how solar modeling is done, I actually had forgotten about this talk. Joyce Gusick in 2020 gave a talk on how this is done. It's on our YouTube channel. It's worth watching, especially if you want to find out about what helioseismology has to do with inferring where that radiation convection boundary is. She actually covers a lot of the details that goes into these models. So as I said, solar abundances now favor a lower metal content than we did in the 90s. But how are these abundances determined? First, we look at spectroscopy of the sun, like I showed you in that first picture with all the absorption lines. We need a good model of the solar atmosphere. You need a 3D rad hydro model that includes non-LTE physics that gives you the line positions of elements you should observe, their intensities, as well as their widths. You need to have all of that consistent. And once you have all of that consistent, you can ask the question, which abundances in my solar atmosphere model, which I've calculated through this rad hydro and this non-LTE physics, gave me the spectrum that matches what I observed in the sun, in the photosphere, in the outer parts of the sun. You can also use meteorites to double check that you're getting the same abundances as photospheric measurements. That's a little involved. For example, we can't determine neon directly from this technique up here. We need to get it from a meteor. Abundances are presented in these logarithmic units, which are scaled to the abundance in hydrogen. Basically, hydrogen is assigned a value 12, and then on a logarithmic scale, metals will be something like 8 or 7. They are way down in mass concentration. Here I have made a quick table. Let's just quickly talk about what this table says. I'm going to show some elements in the left column, and then up top here are some compilations of abundances throughout the years, with the last 2 digits tell you which year they occurred in. At the bottom is the metal fraction in these compilations. You can see that we begin with about 2.5% metals in 1993, and then this red line shows the steep revision in 2009, where we're now at 1.8%, and that slowly creeps up to about 1.9%. Let's take a look here. Carbon. Okay. Carbon seems to have changed quite a bit. Remember, these are logarithmic scales, so small numbers here actually do show some changes. Let's look at oxygen. Oxygen was revised quite a bit down and has remained low compared to the 93 and 98 compilations. Let's look at neon. Neon has gone way down in 2009 relative to the 93 or 98 compilations, but it's crept back up again. There's actually a lot of discussion around neon right now. And let's look at iron, our favorite element here. This was a surprise to me. Iron does not seem to have been revised at all, except in the 2020 compilation by Asplund, where it's gone down slightly. And there are error bars. The error bars are about 0.0405 in the last digit here. And so this was a surprise. It really seems that oxygen being revised down has played a big role, which makes those experiments that were recently published by Jim Bailey all the more valuable. See if I can talk about this. So I found this paper by Gail Bulgen and John-Christoph Payne, published in 2024 in Nature Communications, this helioseismic inference of a solar radiative opacity. This was an interesting paper to me because it asked the following question. I have these standard solar models that can reproduce the location of a radiation convection boundary, provided I do things in a certain way. What would I need to do if I specified an abundance, an equation of state, and whatever else, and I took an opacity model, and I changed the opacities in that model in such a way that I reproduce the location of a radiation convection boundary? That's done through something called the Ledoux discriminant, which relates the thermal and adiabatic gradients of the solar radiation convection boundary. I don't fully understand this. As you can see here, You just iterate until you reproduce one of these standard solar models where things agree. And then you go look at what happened to your opacities. I should say the opacities are related to these gradients over here. And let's take a look at one of our compilations, the opal tables as a function of radius inside the sun. In red is our standard opacity table, and in orange is the modification done through this iterative method to look at this Ledoux discriminant. You see this slight increase here as you approach the radiation-convection boundary, which is on the right-hand side here. That increase is about 15% in the mean opacities. You can break this down further as to which elements need to be corrected. But what do you draw from this? Essentially, if you want to reproduce properties of the sun, you need to do something to the opacities. You need to raise them up slightly. So this is why the astronomers get interested in the Sandia results. Anyway, go read the paper. Very informative. So some final thoughts, and I gave a lot of thought to what I might say here. You're probably wondering, what do we know about opacities today? All the models agree with the experiments at anchor 1. Okay. Now, where things start to disagree are these anchor 1 plus and anchor 2. 1 plus, lower temperature, slightly higher density. That's true for the Z data. In red is the Z data, in black is Scram, one of the opacity models. It's true for our NIF platform, done through Bob Heater, which I saw here somewhere. Now Patty Chow as well. And then bottom here are just some opacity models plotted here. And you can see that all of these models from the TriLab ecosystem, they all basically agree with each other. So that's anchor 1 on the left there. Anchor 1 plus, where we've simply increased the density, you can start to see that Z predicts a higher opacity than our opacity models predict. Same is true on NIF, larger error bars on NIF. And the codes, once again, are roughly in agreement. Our own code, Opus, seems to have slightly higher opacity than the Los Alamos atomic code or the Sandia Scram code. Okay, but 1 plus really starts to show there's a problem. And anchor 2 is still an ongoing discussion. Go see the talk by Jim Bailey I referenced here to see where we stand on that. So earlier in the week, someone asked me, well, what did we actually learn from all these opacity experiments? And this is where I gave a lot of thought. And I like to see it in this little picture. We have experiments, we have theory and models. And why do we separate them like this? Well, the experiments over the last 15 years have really learned a whole bunch of things. How do we create these conditions? How do we diagnose these plasmas? How do we repeat these experiments to show that the platform is repeatable? Z and Sandia has done a fantastic job to show that they are repeatable to some extent. Someone might ask, what happens if we go to NIF? That's why we have platform diversity. So we do these experiments on NIF now to double check what Z is doing. We've learned things like there are temporal spatial gradients in the Z platform. That was published by Guillaume Lozel, I think last year, also a great PRL. And we've also learned a lot about how do you analyze the errors in the opacity measurements, which is work that Tai Nagayama has done. On the theory side, these experiments keep challenging us. So we get to ask questions like, is configuration and interaction important? No, it's not. Los Alamos checked. Do two photons matter? Apparently not. I checked. Some disagreement from other work. Do line shape models correctly predict what we measure? That's actually a very interesting thing. Line shapes, probably we need to look a bit more carefully at. So work that Thomas Gomez is doing is actually very important there. Recently, there's been discussion about occupation probabilities. That could explain some part of the spectrum. Then there are more practical things, code comparisons. Why does Opus give one answer? Why does Atomic from Los Alamos give a slightly different answer? It's all very useful. If you ask Daniel Aberg sitting here, even code design, these codes are tens of thousands of lines long. And they often involve antiquated code written from Fortran 77 and 90 and now C++ in between. This is not a trivial problem. That's why we hire computer scientists to help us. And then just to leave you with a question here, anchor 1 plus, density is slightly higher. Does that mean something? Do we need to start thinking about the role of density in these opacity models? Jury is out on that, but it is an interesting thought to have. I think Last comment I want to make. These two pictures really are the lab ecosystem, but now that I'm getting old and gray, I want to say that they actually touch two other things that are very important. One is the broader community, which you think in this case, the astrophysics community. It's been 30 years since we released the updated OPAL tables. What have we done since then for the astrophysics community? It's been 10 years since Atomic released its table to the astrophysics community. These tables don't come along often, but when they do, they are latched on by the astrophysics community immediately because they don't have the ability to create these tables by themselves. That expertise sits here. You'd go talk to David Katami, he will tell you, gee, they would really like some Lanfonite tables to understand neutron star mergers right now. That's a very difficult problem. On the bottom here, workforce development. I'm in my mid-40s. I joined this work 10 years ago. I'm still discussing the same experiment. The knowledge that people like Carlos and Brian Wilson, as well as the people at Los Alamos, Chris Fonts, James Colgan, the knowledge that those people have that they need to pass on to the next generation is a huge amount of work. You don't just join a group and learn this stuff overnight. It's very complicated physics touching all sorts of physics that you've probably learned sometime in the last 20 years. Developing these platforms also takes 20 years. So in some sense, it's very encouraging for me to see, for example, we have Patty Chow sitting here, one of our HED fellows. It's going to take over some of the work that we're doing at NIF from Bob Heater. That's going to take many years to do. And I want to give a quick shout out to two students that visited us at Livermore, both from the Wooten Center in Texas, Jackson White and Bryce Hobbs. It's really encouraging to see this next generation come up and to be interested in these problems. But for them to be interested in these problems, you need to tell them that, look, you know, you're not just doing some random experiment on some element on some very expensive machine that maybe 5 people in the world care about. There's a whole community out there of astrophysicists that are dying to wait, are the opacities actually wrong, or is it something on our side that's wrong? Okay, on that happy note, I will leave you with questions and encourage you to eat the cookies. Otherwise, Federica's going to put them in my office. And
thank you, Veronika. That was a very nice talk. I'm really glad I twisted your arm so that you will give this talk today. Okay, so we have time for questions. There are 2 questions online. I'll read the first one, and then we can move to questions in the room. And if not, I'll go to the second questions online. So first question from Babak Sadiq. At high temperatures, for any given average ion density, there should be a non-negligible density fluctuation. Shouldn't the absorption from a uniform density be quite different from the one with large density fluctuations? Couldn't that account for the violation of the sum rules?
Trust Babak to ask such a great question. I don't know Babak off the top of my head how to answer that question. I think when we do these calculations, we essentially assume everything is local thermal equilibrium. There are no density fluctuations. It's just one density. So I don't have more comments on that. Daniel is... Okay.
Babak, you simply can't go higher than what the sum rule says. That cold curve that you showed, you can't go higher than that unless you have some serious configuration interaction, borrowing intensity from some other region of the spectrum. But that's a huge, I mean, if you look,
trying to get there.
It's a huge spectral range that you need to borrow from that you don't see in that spectrum. So that's not plausible. Yeah. Here you go. You can't go above that dotted line you see there unless you borrow intensity from somewhere else. And yeah, I mean, and the configuration interaction that scales with the energy difference. So if you have a huge energy difference, that contribution would go down. So yeah, I don't think that's it.
Okay.
Great talk, a lot of detail. Is there any interests in the astrophysics community about opacities, how they affect other kinds of stars,
Yeah.
like red dwarfs or blue supergiants?
Yes, and at least two different topics I can think of. The one that I'm more familiar with is these neutron star mergers. When they happen, they eject a lot of material. And there's a lot of excitement about are neutron star mergers the site of the rapid neutron capture process, or VR process. The way you identify that is you look at the emission spectrum, and if you see things like lanthanides in the emission spectrum, then you can say, look, there must have been some process that occurred here to generate those lanthanides. However, the problem with the lanthanide interpretation is that that material is about 5,000 Kelvin, or half an electron volt, so it's mostly near neutral. And there are no good opacity tables of near neutral lanthanides out there. Los Alamos, through Chris Franz, has done actually a reasonably good job at trying to compute this. I think that would be one area. The other area is white dwarfs, where the role of carbon, particularly I think some aspects of carbon line shapes, could be interesting. White dwarfs are interesting because we use them to date the age of the universe. I think that's another topic that's come up.
Yeah, just a little bit more comment on the carbon and oxygen white dwarf question. There's a Discovery Science NIF campaign oriented towards that. It's similar to the iron. Z just published their oxygen data. We're hoping to get ours. We've got some of ours out. It does not agree with the models for the higher density yet. The opacity matters for very similar conditions because it affects the cooling rate of the star, which is used to determine the age of the universe. And that age does not agree with other ages of the universe. And so if we were to raise the opacity, it would slow down the cooling rate and increase the age of the universe measured by the white dwarfs and bring them into agreement with the other approaches. I did also want to comment, Patty's recent work on the Anchor 1 Plus iron is showing better agreement with the theory at Anchor 1 Plus.
We can get there.
That hasn't been published yet, and we have a bit more work to do, but that's where it's looking right now. So the plot will thicken.
Okay, I'm going to read the questions from Lauren Benedict. Thank you for this wonderful presentation. Question: I didn't hear you mention anything pertaining to continuum lowering. Is that unimportant even at the higher density Anchor 2 conditions? Of course, I appreciate that even an inclusion of continuum lowering may not change the overall magnitudes a lot of the relevant cross sections by enough to do anything here.
Let me get a slide here so that people can understand what we're talking about. Would be a good slide here. So Lauren is asking about plasma effect called continuum lowering. Since these ions are in a plasma, that plasma is somehow communicating to the ion, and it changes what you would typically say is this Coulomb 1/R potential. And what it does is it lowers that potential barrier slightly. So it makes it easier to ionize ions. There are two ways that we currently put this into opacity codes. Two models, one is Stewart-Pyatt, the other one is Ecker-Kroll. We tend to favor Stewart-Pyatt. It's a bit of an ad hoc correction. I don't actually know how we include it in the opacity codes. I was hoping to show here, but what it does is it tends to remove some of these lines here. I think, Lauren, this is an ongoing discussion right now about how do we treat states that are almost delocalized. Those are the atomic states that are appearing right before you ionize the atom. I think there's always open work to be done on that. Sorry, I don't know.
Let me get to another question online, and then I'll go to you. So Patrick Renaudin asks, thank you for this inspiring talk. On slide 31, it is not so clear if the measured line broadening is well reproduced by theories. How is the comparison when passing from Anchor 1 to Anchor 2? Could there any issues in line broadening estimations?
Yes, there definitely could be issues in line broadening estimates. The code that we have at Livermore, called the OPUS code, and our previous codes as well, we use the semi-analytical fits from Konchevik and Dmitriev. These are not super detailed line shape calculations like you might get from a code like Merle or codes that Thomas Gomez has developed. You can see here that, I need to point here quite carefully, blue is the opacity model and red is the experimental data. And you can see that the opacity model seems to have a narrower line width than the experimental data suggests. And this particular region of a spectrum over here, is right over here, if these n equals 4 transitions, has been concerning to us for line shape models. We don't have a good answer to this, or at least in our group, we don't have a good answer to this right now. Part of the difficulty is that running a more detailed model like Merle is computationally expensive for those lines, if not borderline impossible. Just if you have more questions, feel free to email me about that. I think the line shape work is something that we should look at a bit more carefully.
We have another question online. Dwayne Little asks, do you know if the funding from NASA, the astro community, is proportionate to the efforts of the national labs? Should it be?
I do not know such things. I think NASA historically has had relatively little money compared to the national labs, and potentially now has even less money. That's why I don't know the answer to that.
Thank you. Any other questions in the room or online? If not, let's thank Veronika again. Thank you everyone for coming to today's seminar. I hope to see you next time.